My name is Thomas Mitchell, and my collaborators are Noam Agerman, Vladimir Kim, and Michael Kazdan, and here I'll be discussing our recent work, Möbius convolutions for spherical CNNs. So, Möbius convolutions enable the construction of spherical networks that are equivalent to Möbius transformations. And so it makes sense to ask, why should we care? Why are Möbius transformations interesting to us? So one area in which Möbius transformations are interesting is in the context of shape analysis and recognition. And often in applications, a lot of the shapes we'd like to analyze with the convolutional framework are related by a type of shape deformation called isometries, transformations that preserve distances. So existing state-of-the-art surface CNNs are isometry equivariant and have excelled in fundamental geometry processing tasks such as shape classification, segmentation, and correspondence. However, these networks fail to achieve adequate performance in the presence of complex deformations, like those commonly found in real-world data. Such deformations may be better modeled by less restrictive transformation groups, such as Möbius transformations, which preserve angles but not areas. They encompass a broader class of deformations than isometries, while still preserving shape fidelity. So Möbius transformations are also interesting in the context of omnidirectional imaging, as they're the spherical equivalent of homographies. For example, suppose we're viewing a 3D scene with a spherical camera, in this case a car, and we capture it by taking a 360-degree image with our camera. Then, if our spherical camera undergoes a small rigid transformation in 3D, say we move a bit to the right and then rotate our camera a little bit, and afterwards we capture another image, the transformation relating our two spherical images will be well approximated by a Möbius transformation. And despite their success in a variety of tasks, existing spherical networks are only equivariant under rotations, which are the isometries of the sphere. And it makes sense to ask whether moving to Möbius equivariance can provide benefits in spherical imaging tasks. Okay, great. We've got a good handle on why Möbius transformations are interesting. But what are Möbius convolutions? Möbius convolution is a flexible and descriptive spherical convolution operator that is equivariant under Möbius transformations. So, what does Möbius equivariance mean? For example, let's consider a spherical signal, in this case an omnidirectional image, and we'll pass it through a Möbius convolution with an arbitrary filter, after which we'll get the response on the right. Now, let's transform the input image by some arbitrary Möbius transformation. Then, if we pass the transformed image through the same Möbius convolution, the new response will be equivalent to the original response transformed by the same Möbius transformation as the input. In other words, Möbius convolutions commute with Möbius transformations of the input features. So, how do they work? What goes into a Möbius convolution? So, Möbius convolutions are part of the extended convolution framework, which allows filters to adaptively transform as they travel over a domain. So to understand the mechanics of Möbius convolutions, we'll first look at rotation equivariant extended convolution in the plane, which shares the same basic ingredients. Then, we'll see what we need to generalize to Möbius equivariant convolutions on the sphere. So, like standard convolution, extended convolution takes two inputs, a signal and a filter. The signal is our input data, an image, network features, etc. The filter is a function which assigns weights to different points in space. Where extended convolution differs from regular convolution is that the input signal is passed through both a frame operator and a density operator before computing the convolution. The role of the frame operator is to map the input signal to a frame at each point in the domain, which is used to align the filter. Here, each frame is a rotation, which you represent visually by a direction vector specifying the x-axis of the frame. The density operator maps the input signal to a distribution-like quantity, which is proportional to the area measure. So like regular convolution, extended convolution slides the filter across the signal. To compute the response at each point, neighboring values are weighted by evaluating the filter at the relative position of the point as seen in the neighbor's coordinate frames. For each neighbor, what we're doing is 1. Consider the relative position of the point with respect to the neighbor. 2. Express the relative position in the frame at the neighbor. And 3. Evaluate the filter at the transformed position to weight the value of the signal at the neighbor. So, what makes extended convolution equivariant? What makes it repeatable up to rotations and translations of the input signal? To ensure equivariance, the frame and density operators have to satisfy specific properties. In particular, the frames assigned to each point must rotate with the signal. This way, the frames will always align the filters in a manner correcting for the local rotation of the signal. So, how can we define a frame field that satisfies these properties? Well, what we'll do is we'll take our input signal, compute the gradients, and use their direction to encode a frame at each point. This works because the gradients rotate with the signal, so our frame operator will have the desired property. Like the frame operator, the density operator also needs to be repeatable up to rotations of the input signal. And while it isn't necessary for rotation equivariance, we also want our density operator to satisfy an additional property. Namely, the density operator needs to scale inversely proportional to the local change in area induced by a transformation. This way, the density distribution controls for the change in area measure when integrating against the aligned filters. To construct this operator, we can use the squared gradient magnitudes, which scale inversely proportional to the change in local areas. So, what do we need to generalize extended convolution to Möbius equivariance on the sphere? First, we need a way to parameterize the sphere about each point. This will allow us to describe the relative positions of points. Second, we need to define a Möbius equivariant frame operator. Here, the frame operator will assign a Möbius transformation to each point in the sphere, which will be used to repeatedly align filters. Möbius transformations are conformal, and so they aren't area preserving. The final ingredient is a density operator controlling for the conformal scale factor induced by Möbius transformations. In what follows, we'll give a generalized overview of each of these components, leaving the details to the paper. To define a local parameterization about arbitrary points in the sphere, we assign to each point a transformation which we call the generalized logarithm. Here, the generalized logarithm at each point is a rotation that takes the point to the North Pole, which we view as the origin. This rotation isn't unique, but it doesn't have to be, as long as it's defined consistently. For example, consider neighboring points P and Q on the sphere, shown here. The generalized logarithm of P is the rotation around the z-axis, followed by the rotation around the y-axis, taking P to the North Pole, consistent with the standard spherical coordinate parameterization of the sphere. Then, we can view the position of Q with respect to P as the transformation of Q by log P. In practice, we associate the sphere with a compactified complex plane via stereographic projection from the North Pole. Here, the generalized logarithm maps each point to the origin, and we think of its image as analogous to the tangent space at each point. So, how do we define a frame operator to align filters repeatedly in the presence of Möbius transformations? So here, we'll present the key insight and leave the details to the paper. Given a point in the sphere, which we'll take to be in the center of Jupiter's storm, the generalized logarithm maps us from the sphere to the tangent space at the point, giving us a description of the relative positions of neighboring points. Now, applying arbitrary Möbius transformations to the sphere, we can use the generalized logarithm to view the corresponding deformations of the tangent space at the transform point. So these are the deformations we need our frames to correct for, and what we can observe is that these deformations leave the origin fixed. This follows intuitively from the fact that the generalized logarithm maps transform points to the origin of their respective tangent spaces. And this means that our frames belong to the lower dimensional subgroup of Möbius transformations that preserve the origin. And in practice, we recover the frame operator from the gradients and Hessians of the input features, and the details of the construction can be found in the paper. So, this leaves us with the density operator. And unlike rotations, Möbius transformations are conformal, which means they preserve angles but not areas. Specifically, local area distortion induced by Möbius transformation is measured by the conformal scale factor. Regions the transformation contracts have a large scale factor, signifying high compression, and regions the transformation expands have a small scale factor. Fortunately, using the squared gradient magnitudes will give us a density operator proportional to the conformal scale factor. This will ensure the density distribution controls for the change in area measure induced by a Möbius transformation when integrating against the aligned filters over the sphere. Now, to build CNNs with Möbius convolutions and use them in real-world applications, we need to be able to compute Möbius convolutions accurately, efficiently, and at scale. Otherwise, they aren't going to be very useful for us in a practical sense. So, to do this, we develop an implementation based on the fast spherical harmonic transform. And this part is pretty tricky, but leaving the details to the paper, the basic idea is that we choose a specific basis for our filters that have special symmetry properties in relation to the origin-preserving Möbius transformations defined by the frame field. We exploit these symmetries to approximate the transformation of filters as linear combinations of the basis functions, which allows us to expand Möbius convolutions as sums of simpler convolution-like operations, each of which can be computed via the fast spherical harmonic transform. So, how do we build CNNs with Möbius convolutions? Well, it turns out to be pretty straightforward. Möbius convolutions are modular and self-contained, and the basic building blocks are the same as in standard CNNs: a convolution followed by a normalization layer and a nonlinearity. Specifically, layers take scalar features as inputs, which are then passed through a Möbius convolution block, whose output is also scalar features. Then, the features are passed to a normalization module. Here, we use filter response normalization, which divides each channel by its squared mean. However, out-of-the-box filter response normalization isn't Möbius equivariant, and we modify it to preserve Möbius equivariance by replacing the squared mean with the Dirichlet energy. Afterwards, we apply nonlinearities pointwise. These could be in the form of standard activation functions, though we use thresholded nonlinearities, which have been shown to specifically complement filter response normalization. So, now the question is, are these networks actually Möbius equivariant? And the answer is yes, approximately. We set up a simple equivariance experiment where we pass spherical features through randomly initialized layers. For each initialization, we applied a random Möbius transformation with a fixed scale factor before and after passing the features through the layer, and defined the error as a normalized L2 difference between the two outputs, essentially measuring the degree to which the layer commutes with Möbius transformations of increasing severity. In addition to our proposed approach, which is shown in green, we evaluate a standard 2D convolution layer as a baseline, shown in red, which treated spherical data as a 2D image. We also considered two layers consistent with our proposed approach up to restricting the frame operator to only rotations and dilations, shown in blue and yellow respectively. We can see that the equivariance error of our proposed approach, wherein the frames belong to the origin-preserving subgroup of Möbius transformations, stays very low, even in the presence of significant changes in scale. Notably, we also see that restricting the frames to only rotations, or even rotations and dilations, fails to well characterize the local deformations induced by Möbius transformations, even when the scale factor is relatively small. So, what kinds of things can we actually do with the Möbius equivariant network? So, one neat thing we can do is to conformally map genus-zero shapes to the sphere, which allows us to use Möbius convolutions as a tool for conformally aware shape analysis. As an example, we use Möbius convolutions to classify 3D shapes from the popular Shrek 11 shape classification dataset. Recently, state-of-the-art surface networks have achieved outstanding classification accuracy on this dataset, and to better gauge the strengths of our approach, we created the second version of the dataset by applying random conformal transformations to augment the meshes, something prior methods aren't built to handle as they're only isometry equivariant. And while we matched state-of-the-art performance in the original dataset, we significantly outperform other methods in the conformally augmented version. This suggests that a new class of conformally aware networks have the potential to outperform existing isometry-aware approaches in challenging shape analysis and recognition tasks. We can also use Möbius convolutions as a tool for the analysis and processing of omnidirectional images. As an example, we applied them to segment omnidirectional images from the Stanford 2D 3DS dataset. In many ways, this is a challenging task for our framework. Equivariance is devalued due to the consistent vertical orientation of the images, and spectral aliasing can oversmooth the sharp features necessary to make accurate predictions in the presence of the large class imbalance. Despite these challenges, we still attain performance comparable to existing state-of-the-art approaches, and outperform the top-performing spectral approach, spin-weighted spherical CNNs, which is only rotation equivariant. Here, we introduce Möbius convolutions, which provide flexible and modular building blocks for Möbius equivariant spherical CNNs. We believe they have the potential to be utilized in a wide variety of tasks across geometry and image processing. We hope they serve as the catalyst for the development of a new class of conformally aware networks. Thank you for watching.